This video is going to look at various properties that are impacted by intermolecular forces, the first of which is surface tension, and I will show you a sample of this in class shortly. Basically, surface tension is resisting an increase in surface area. When you have a stronger surface tension, you're going to be able to hold things on top of your surface more easily than you would if you have a smaller surface tension. So water works really well. It has fairly high surface tension. The stronger the intermolecular forces, typically the higher your surface tension. Water, having hydrogen bonding, has one of the stronger intermolecular forces. So we tend to see polar molecules being able to hold things on their surfaces more easily than nonpolar molecules such as oils. Capillary action is a way to move a liquid up a tube spontaneously. Capillary action kind of helps to explain how thermometers work. It's also how you could use a thin tube to pull to tap a little bit of liquid in and it would move upwards. What allows this to happen is it has to do with the polarity of the substance that's moving up the tube and the polarity of the tube itself, which typically will be glass. When the two forces are opposite, when you have intermolecular forces present in something like mercury as opposed to glass, which is polar, the nonpolar mercury is going to have London dispersion forces. The polar glass is going to have both London dispersion and dipole-dipole forces. We tend to see a convex meniscus, one that is facing up, because the mercury forces want as little to do with the glass as possible, and so they oppose it. So we have what's called cohesive forces. This isn't something that I'm going to ask you guys to know a whole lot more about beyond just what capillary action is. But I thought it might be interesting for you to see why thermometers have a meniscus facing up versus alcohol-based thermometers that have a meniscus facing down. We see adhesive forces dominate with something like alcohol or water and glass because they have similar intermolecular forces. They both tend to be polar, so they'll have dipole-dipole forces. With water, we will see that hydrogen bonding become involved. And so we will see a little bit more of attraction for that liquid towards the side of the container in which it's being held. And so the meniscus is going to be concave, it's going to face down. Viscosity basically is how well you flow. So like syrups and things like that don't tend to flow nearly as easily as things like water. We see substances typically with larger intermolecular forces that are more viscous than those that aren't. And the larger your substance is, typically that's going to increase your viscosity. So viscosity is basically you don't want to float. Vapor pressure is the pressure that you have of the liquid when you are at equilibrium, and when the vapor pressure of the surroundings equals the vapor pressure of the liquid that's trying to escape to become a gas, you will have boiling. When it's not quite there, you will see some evaporation taking place. And the amount of vapor pressure that you have present is going to depend on what type of forces are making up your substance. Substances with weak intermolecular forces are more easily able to reach the surface. They are called volatile liquids, and they have higher vapor pressures as a result, whereas non-volatile liquids have to overcome stronger intermolecular forces to reach the surface, and therefore not as many are able to achieve that, and they have lower vapor pressures. So this is just an example of a graph relating vapor pressure to temperature. On the previous slide it talked about how temperature, as temperature increases, vapor pressure increases, and we see this for both the volatile and the non-volatile liquids. Volatile would be diethyl ether. If we pick a temperature, we see that diethyl ether has a substantially higher vapor pressure than water. Water being non-volatile at a given pressure will have the highest boiling point of the three liquids. It will have the strongest forces to overcome in order to be able to escape to become a gas. We can relate the vapor pressures to temperature with a relationship that's similar to the one we used in our kinetics chapter with activation energy and rate constants and temperature. It's called the Claudius-Clapeyron equation, and it ought to look very similar to the one I just talked about, but we're going to save that one for our next video. Melting point obviously is when we change over from a solid to a liquid, but what's actually happening when you are melting is that you're able to break out of that lattice structure and not be in such a rigorous form and able to change over to be a liquid. We do not see the temperature changing, so we have a constant temperature. We don't see the kinetic energy changing, only potential. This happens when the solid's vapor pressure is equivalent to the liquid's vapor pressure. And what we use to determine how much energy has to be required to overcome those intermolecular forces is what's called the heat of fusion. So in order to break out, you have to eliminate those intermolecular forces that are connecting between the molecules so that ice can turn into water, or any other sort of crystal could become a liquid form. With boiling, as I talked about previously, that's when your liquid's vapor pressure needs to be the equivalent of the atmosphere's vapor pressure. What we use to determine the energy required to overcome those intermolecular forces to transform a liquid into a gas is called the heat of vaporization. It too is going to happen at a constant temperature. So just to review, this is a heating curve for water. We see that there are flat lines and we see there are sloped components. The sloped components are where you are staying in the same phase. Your temperature is changing, but your phase is staying constant. When you are transforming between phases and overcoming those intermolecular forces, we see the flat lines at 0 degrees and the 100 degrees representing the phase changes. So in this set, I ask you to tell me which one would have the highest boiling point and why. All of these contain carbon. We've got 4 chlorines on one carbon, carbon tetrachloride, 4 chlorines, 4 fluorines, and 4 bromines. So carbon tetrachloride, carbon tetrafluoride, and carbon tetrabromide. All of these are going to be nonpolar by nature because they are all formed with the same types of atoms connecting their molecules together. The largest one will be CBr4 because the bromine atoms have a larger size. And because of that, since these only have London dispersion forces, the larger atom is going to be more easily polarizable, and so CBr4 would have the highest boiling point of these 3 choices. And again, that's because with the more electrons, we are more likely to have an instantaneous dipole, and we're going to see those electrons end up on one side of the bromine atom a little bit more than we would in chlorine or fluorine. If you need to pause, please do so now, and as always, please write what you feel you need to write down. Here we have CH3OCH3, this is dimethyl ether. We have ethanol, and we have propane. And we're asked which of these would have the smallest vapor pressure. So again, the one with the smallest vapor pressure is going to be the one with the strongest intermolecular forces, because as we saw before, when you have weaker intermolecular forces, it's easier for you to escape and become a gas. You don't have as many forces to overcome, so you're able to get there with a higher vapor pressure. So with these 3 choices, propane is nonpolar, so all it's going to have are London dispersion forces. With that in mind, it's going to require its forces are very weak, so it's going to be easier for it to escape and become a gas, so it's going to have a higher vapor pressure than we would see perhaps in these other 2. In dimethyl ether, we have some symmetry, but we also have this oxygen atom in the center, which is going to cause the molecule to be slightly polar. There is no hydrogen bonding possible in this molecule, so this one is going to have dipole-dipole forces, which is going to cause more of the molecules to require energy in order to break those intermolecular forces. So this one will have a little bit higher of a vapor pressure, or excuse me, a little bit lower of a vapor pressure than propane, but not as low as ethanol will, and that is because ethanol has hydrogen bonding. And because ethanol has hydrogen bonding, that molecule has substantial intermolecular forces that it has to overcome to be able to escape and become a gas. And so it is going to require a tremendous amount of energy for those to be overcome, and it would have a much smaller vapor pressure than the other two because not nearly as many of the molecules would have been able to achieve that. Sorry, I get tripped up on this one. So let's try one more time. Propane is nonpolar. It has London dispersion forces which are easily overcome, so it's going to have a higher vapor pressure. Dimethyl ether is going to be slightly polar, so it's going to have both dipole-dipole and London dispersion forces to overcome. The dipole-dipole forces are a little bit stronger, so it's going to have a slightly smaller vapor pressure than propane, whereas ethanol with a hydrogen bonding is going to have the strongest intermolecular forces to overcome, and therefore the fewest molecules that will have achieved reaching the surface and will have the smallest vapor pressure. Let's try another one. Viscosity. Here we have H2S, HF, and H2O2. All of these are polar molecules, so the first force we're really going to take a look at is dipole-dipole. We have H2S, which is a bent molecule. Sulfur would have 2 lone electron pairs on the sulfur atom. We have 3 lone electron pairs on the fluorine atom for hydrogen fluoride, and then we have 2 lone electron pairs on each oxygen atom in hydrogen peroxide, H2O2. H2S is going to kind of get lost because both HF and H2O2 have hydrogen bonds that are available, and so that's going to be a stronger intermolecular forces than just the dipole-dipoles that are present in H2S. HF has one location between the F and the H where it can form hydrogen bonds, whereas H2O2 has 2 atoms, both oxygens can form hydrogen bonds with adjacent hydrogen peroxide molecules. So hydrogen peroxide is going to have the greatest viscosity because it has multiple sites for hydrogen bonding compared to HF. If that had been H2S2, HF would have had the greatest viscosity because it would have been the only one that could have hydrogen bonded. Here we have the smallest enthalpy of fusion, so which one has the fewest forces to overcome. We have I2, CSVR, and CaO, so cesium bromide and calcium oxide. Iodine is nonpolar, so it's just going to have London dispersion forces. CSVR and CaO are ionic compounds, and they are going to have electrostatic forces. Iodine's forces are the weakest of the bunch, and so as a result it's going to be able to escape and become a liquid more readily, albeit it's still going to take time because of the London dispersion forces and the larger sized atom, which is going to increase its polarizability compared to cesium bromide and calcium oxide. But those electrostatic forces are going to dominate. And that is the end of this video, and again I'm really sorry about that one example with the vapor pressures.